All right, let's start off with something a little bit much the same. So these are odd degree functions, and now hopefully what am I going to be focusing on in this is I'm trying to get us to understand what this means. That's all. It's the goal of the next 7 minutes and 13 seconds. That's how long this video will be. Anyways, odd degree functions. We're going to look at the left-hand and right-hand side behavior. Now, we talk about left-hand side and right-hand side behavior. So for instance, I'm just going to put a box around here. When I'm talking about the left-hand and right-hand side behavior, I know that my function will behave like it'll be either increasing or decreasing on the left, and then it may be increasing or decreasing on the right. In the middle, it'll have a whole bunch of terms. But when I put together the information of the leading coefficient and whether the degree is odd or even, I can determine the left and right hand side behavior, which is exactly what I want. All right, let me erase this nonsense and let's get back to business here. Odd degree functions. If the leading coefficient is positive, the graph is increasing from the left and increasing as it exits to the right. So, when I use the word increasing, it means has a positive slope. So, for example, all odd degree functions. Now, this is a bold statement here. Odd degree functions, so 2x plus 1. Y is equal to 2x to the 5 plus dot dot, a whole bunch of garbage, plus 1. Y is equal to 2x to the power of 3, a whole bunch of stuff. Oh, let's make it minus 4. It doesn't matter. When our degree is odd. So this degree is 1. When my degree is odd. 1, 5, 3. And my leading coefficient is positive. 2, 2, and 2. So here, let me switch it up. Let me make this 3. Big change. So when those two conditions are met, the graph is increasing from the left and increasing as it exits to the right. So what do we know about all of these graphs? Well, it may behave different in the middle of a graph, but the extreme left will be increasing, have a positive slope, and the extreme right will be increasing. It has a positive slope. Now, how do I know that? How do I remember that? I just think of, I'm the master of a linear function. When my leading coefficient is positive, it overall has a positive slope. On the other hand, if my leading coefficient is negative, the graph is decreasing from the left and decreasing as it exits to the right. So, again, what happens in the middle of the graph? I have no idea. Well, I mean, I do, but that's a conversation for later. My graph will be decreasing from the left and decreasing to the right. That's it. So, for example, y is equal to negative 4x to the power of 17 plus dot, 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 dot. And it doesn't matter what these next terms are. I could have 17 more terms and then plus 4. What really matters here is that my leading coefficient is negative and my degree is odd. That will be the behavior of the left-hand and right-hand side. All right. Now, with analogy, like I always think of, what? I always get this confused. So I just make up an example that is an odd degree function that I'm super awesome at. What just happened? So I'm super awesome at this odd degree function here. Right? It's a linear function with, and I know that when my leading coefficient is negative, it'll have an overall negative slope on the left and the right-hand side. By the way, we call that decreasing. And we have to get used to the words like increasing, decreasing, really helpful in physics, for instance, right? Also, in calculus, we're going to be using tons of those terms. Who doesn't love a good calculus conversation from now and again, eh? All right. Let's switch it up. When my even degree functions, oh, are you the master of even degree functions? Yes. Think quadratics. So if the leading coefficient is positive, the graph is decreasing from the left and increasing from the right. It might be helpful to create an example here. So y is equal to 2x squared plus 1. Now, it doesn't matter what that middle term is. What am I saying? Is you know instantly, since a, the leading coefficient here, we call this a in quadratics, you know that if that was positive, the parabola would open upwards. And with all even degree functions, the graph from the left is decreasing. Now be careful, a lot of people have a hard time with saying that it's decreasing. Overall, it has a negative slope. And on the right, it will be increasing. Overall, this is upward opening. I don't really love that term, upward opening, because we don't really use it beyond grade 11. But it aptly describes the situation, though. If the leading coefficient is negative, the graph is increasing from the left and decreasing to the right. Now, words are a little bit tricky here. So I'm just going to write where my leading coefficient, hopefully my pen works here, y is equal to negative 2x. Now, I could put negative 3, negative 4, it doesn't matter. My leading coefficient just has to be negative. Minus 1. What do we know? Well, or, let me just make one crazy one here, right? This, by the way, this is this example, giving this white space. Y is equal to negative 5x to the power of 16 plus plus many other terms. If my leading coefficient is negative, which is here, and my degree is even, which it is here, what do I see? That my graph will look like this. Now that's a terrible, ugly graph. I apologize. But from the left, my function is going to have an overall positive slope. On the right, my function will be decreasing. So this is an increasing function, that's a decreasing function. So what happens in the middle? Likely a bunch of curves and zeros and stuff like that. We'll worry about that later. All right. Formal definition. Oh, by the way, in math, the formality of math, of a math textbooks, usually is very intimidating to students. I've always found that once you understand the formality and once you get used to speaking very formally in math, the math becomes much, much easier. Why do mathematicians speak with such formality? It's because this is the best and most concise way to communicate the ideas. So try to get used to formality if you plan to study math or take math courses, because it doesn't go away. Formal definition. If a function is increasing, or a function is increasing if f of x2 is greater than f of x1 and x2 is greater than x1. What are we talking about? So I'm just going to say my function is increasing. I'm just going to put 2 points. My x1 is here, my x1 is less than my x2, or my x2 is greater than my x1. And if my f, my y value of x2, is greater than my y value of x1, that's an increasing function. That goes along with that conversation. That's what we mean by increasing. Now, you can say it has an overall slope. However, slope is only used really to describe between 2 points. So if you have a curve, the curve doesn't have a slope. But if you take 2 points between that curve, you can describe it as a slope. It becomes very important in calculus. Now, if f of x2 is less than f of x1 and x2 is greater than x1, okay, now I'm just going to say here, I'll start here, x1, x2. Right? x2 is greater than x1. However, if f of x2, the y value with x2, is less than the y value of f1, our function is decreasing. And that's what we see. Anyways, don't be afraid of notation. Try to read it for what it is. It is beautiful, and it really, really makes, this conveys a lot more information in it than saying positive or negative slope. I hope you enjoyed today's lesson. I just want to go all the way up to the top just to describe something. I'm going to take us all the way back to here. A polynomial function, what it's saying is that our exponents all have to be whole numbers. If you have negative exponents, you no longer have a polynomial function. If you have a square root function, no, even just one term is not a polynomial function. If you have a rational exponent, not a polynomial function. I hope you enjoyed. Let us meet up when we discuss 3.2.